So we've implemented this MS-EVB trick in Tinker. This is actually what my colleague Barry Carpenter has been using extensively over the last year or two. And so I'm just going to give you a brief demo of how this works before I close here. So Tinker, for those of you who don't know, is a computer software application for MD simulations, and it's set up as a set of callable routines which allow manipulating coordinates, evaluating potential energies, calculating derivatives, by all the standard MD tricks that people are familiar with. And it's maintained by Jay Ponder's lab. Here is the official website for Tinker. I should say that my MPI version of Tinker is not folded into the official release at this stage. It's sort of a separate branch that we've been maintaining over here, which people are welcome to look at if they like. So to build the Tinker EVB code, I should say, so it's available on SourceForge. There's a subversion repository here, okay? Here's the URL of that. So you can, if you want to play with it, you can download it there. Building it, I'm not going to go through how to build it right now. And the reason I'm not going to go through how to build it is because to build it, it requires installing a version of MPI. So I've done this lots of places, and I typically use OpenMP, which I found to be very easy. There's a few compiler flags that you have to set for your system. You compile, and then it gives you MPI. And so crucially, it allows you access to an MPI parallelized version of the standard Fortran compiler. And then once you have MPI, then building the EVB enabled version of Tinker is effectively identical to how you'd build normal serial Tinker. So in the release that's on SourceForge, you can do it in both 32-bit and also 64-bit. And here's 32-bit commands, and here's the 64-bit commands. And I just want to emphasize that if anyone here has compiled Tinker, you will see that these steps, /compile make, /library make, /link make, are literally identical to what you would do if you were just compiling serial Tinker. Okay, so to set up a standard Tinker job, you typically require 2 files. You require, if you want to do a calculation on some molecule, you need a .key file, which is keyword input for your molecule. And you need a .xyz file, which has the geometry and the connectivity for your molecule. And then if you wanted to do something, say you want to run you want to evaluate the potential energy of that molecule, Tinker does that in a subprogram called analyze. So you do something like /analyze malonic, and then E means calculate my potential energy. So that's how you do standard Tinker. Okay, so Tinker, EVB enabled Tinker is effectively the same philosophy, okay, except that now instead of just 2 files, I need 2 files per replica, okay, where a replica I effectively is just how many diagonal elements I have on my EVB matrix. So I spans 1 to n, where n is the dimension of H. So now the labeling is a little bit important here, okay? So now I have to set up a molecule _I .key file and a molecule _I xyz file for each replica. And so if I have specific keywords, say to calculate the potential energy surface of the potential energy of one replica using some special Tinker functionality, I can specify it in that keyword file. And then, of course, each of my molecular diabatic states has a different connectivity, so I specify them there. Okay, and then there's one additional file that you have to add, which is molecule.evb. And this just has the keywords that tells Tinker the MPI-enabled Tinker, how to construct the EVB matrix from the molecular diabatic states that you've specified with your _I notation. And then when you want to run, say, a potential energy surface job, it's very similar to standard Tinker, except now you're running it in MPI. So you do MPI run -n2, where again, this n and this number here corresponds to the dimension of H. So if I have a 2x2 matrix, it's 2 -n2, and then analyze.x malonic.e, right? Just like you'd see here, except now I'm launching this from MPI. And so once you compile OpenMP, it will give you access to MPI run. Okay, so how it all works, this is just a quick schematic, which is probably pretty obvious, but effectively my, so if I have a matrix spanning 1 to n, I'm going to have 2 files for each of my diagonals. right? Molecule 1, molecule 1, molecule 2, X, Y, Z in key in both cases, molecule N, molecule N. That tells Tinker how to calculate the potential energy surface elements of the diagonal. And then my molecule.evb file contains instructions for calculating these diagonal shifts. So these are just for shifting the relative energies of the diagonal with respect to one another, which can sometimes be important. And then my off-diagonal coupling elements. So that's what molecule.evb includes in it. Okay, so I'm going to go through a really simple example. So for malonaldehyde, just to show everyone how this works. So malonaldehyde is a molecule that a lot of people have looked at, and a lot of people use it because it's easy to represent in both configurations with standard MD force fields. So we're just going to be looking at this H transfer process. Pretty self-explanatory. If you go to the SVN repo that I showed earlier, this example, everything I'm going to show here lives in this directory, malonaldehyde example. And I should say this is a toy example here. Okay, I just put in some coupling elements. I did not worry in detail about fitting my parameters to CCSD TF12 calculations or anything. This is just a toy example to show you how it works. Obviously, if you want your EVB surface to be very accurate, then you have to fit your coupling elements to geometries calculated using a method that you have reason to believe is very accurate. Okay, and that's what we've done in the previous papers, and you can look at those if you want to figure out how we've done that, but it effectively just amounts to some sort of nonlinear least squares algorithm. Okay, so here's the file structure for this malonaldehyde. So I've shown the atom numbers for the two different, this is just a 2x2 case. So here's my reactant configuration, here's my product configuration. I've shown you the atom numbering. Okay, the malonic.1 key file and the malonic.2 key file for both of these. I'm doing a transition state optimization and a frequency calculation, so I have to tell Tinker the saddle point. And again, this is just standard Tinker input. But now if I want to do EVB, I have to put one additional flag in my .key files. I just have to say, okay, when you calculate energy, use EVB. So I put EVB, EVB. And then here's my malonic.1 XYZ file and my malonic.2 XYZ file. The geometries here, the coordinates are identical, and they have to be, because it's meaningless to have different coordinates. And so the code we've written will actually check if these coordinates are identical, and it will throw out an error and say, hey, I think you made a mistake because you gave me non-identical Cartesians. Okay, so have to be identical. If they're not identical, you will be scolded. And then here's really the crucial bit, right, is the connectivity. So in Tinker, this is the atom type, which is force field specific. Okay, and then this is the connectivity. So this is what atoms is my atom 1 connected to. He's connected to 2, 3, 6. Okay, and so crucially here you see that this connectivity here, I'm not going to go through and prove it to you, basically corresponds to this molecule. So you see that atom 4 is connected to 2 and 9. Atom 4 is connected to 2 and 9. Here, atom 5 is connected to 3 and 9. Atom 5 is connected to 3 and 9. Okay, so these are the connectivities for these two different states. This is it. And then my malonic.evb file says, okay, shift my diagonal for my malonic 1 by 0, shift my diagonal for my malonic 2 by 0. Okay, so that's not very interesting, but it just shows you what the syntax is. And then it says do the coupling with a one-dimensional Gaussian that's a function of the difference between two coordinates. Okay, and so the syntax for this is described in the EVB in the documentation that goes along with the subversion repository. But effectively, that difference between the distances is defined by distance 4, 9 and distance 9, 5. So that's this distance 4, 9, 9, 5, and this is a Gaussian that's just centered it there. This is the amplitude of the Gaussian. This is the center of the Gaussian, so 0, so it's perfectly symmetric. And then this is the width of the Gaussian. Okay. And EVB coupled diff1D. 1, 2 means couple state 1 to state 2. So this is just my H12 off diagonal matrix element. Okay, so now I'm just going to give you a quick example of how this works. And then that's basically it. I just want to show you how it works really quickly. So here's my console. All right. So if you go to the subversion repository, what you'll see is effectively that this is the stuff I'm going to have in my malonaldehyde example directory. Okay, so I have already, so when Tinker compiles things, it's going to generate all the executables in the source directory. So the first thing you have to do is you have to copy those executables into the directory of interest. Okay, so I'm going to do that. Copy it here. So Newton in Tinker does optimizations. Vibrate does vibrational analysis. Analyze does potential energy surface, just those single point energies. And dynamic runs MD simulations. So dynamic.x here. Okay, so I have all my executables, .x. I have them here. All right, now what I'm going to do is, so I should say I've set this example up. Obviously, to do a transition state optimization, which is what I'm going to do right now, you have to have a geometry that's relatively close to the transition state. So I've already done that. I have a geometry which is relatively close to the transition state, so that you don't have to watch me struggle in vain to try to prove to you something. And what I'm going to do now is I'm going to do the transition state optimization. So I should say this is just a little script that I've written, which just copies the right files and things to make the jobs for the transition state optimization. Then it runs an optimization, and then it does a frequency calculation. So I'm just going to run that. Okay, so you see Tinker runs. It's all the conventional Tinker output that you probably know and love. And so it's optimized transition state. So this is my vibrational frequencies. And so you see that, you know, I get what I expect. I have one imaginary frequency at the top of my transition state. You know, these are all my zero. I have 1, 2, 3, 4, 5, 6 zero frequencies, which is exactly what I expect from my rotations and my translations. And then these are all the rest of my internal mode frequencies. Okay, and so you see, there you go. I just did a transition state. So my EVB surface is working. I have singing and dancing forces. Okay, so now I have a transition state. Now another thing I want to do is I want to optimize the reactant and the product state minima. Okay, so for that, first I'm going to generate the jobs. So I'm going to copy the geometry that was, I'm basically just going to generate the geometries displaced off the transition state, and I'm going to tell Tinker to minimize each of the minima either side of the transition state. I'm going to do that. So I just generated the jobs, so they're there. Malonic optimize the product, optimize reactant, and then I'm going to do / minima opt frequency. So now this is an optimization and a frequency calculation. And then I do it. Okay, and it runs. All good. Now let's look at the results real quick. I'm just look at the reactant optimization. Okay, and we look at the reactant. So it's optimization. Okay, so it terminated normally. Let's look at the frequency output of the reactant. Malonic reactancy frequency. Yeah. Here we go, vibrational frequencies. And lo and behold, they're all positive. So again, I have my 6 zero eigenvalues, and then I have my vibrational degrees of freedom. And this, I've just shown you the reactant. The same is true for the product, and you can verify that if you want. I'm not going to show that to you right now. Okay, so we've done that. Let's do a little dynamic simulation. So I already have dynamic X calculated. I'm going to generate input for the dynamics, and I'm going to initialize this dynamics at the top of the transition state. And then I'm going to use my MPI run command to run 99 steps of dynamics, okay, with a 1 femtosecond time step. I'm going to dump every femtosecond, and this 1 tells Tinker to do an NBE simulation. Okay, so I did that, and one of the things that it generates, now I'm going to make a movie that I can look at in VMD with this script I've written. So what this does, it just takes all the Tinker output and it just ties it together and makes a movie. Okay, done. So now I have this file, dynamics movie vmd.xyz. So I'm going to show you what that looks like in VMD. So I've already loaded it. Oh, great. What just happened there? There we go. Okay. So I'm just going to hit play on this movie. And so there you go. You see I've done a dynamic simulation that initialized at the top of the transition state. And because I'm coming off the transition state, I have vibrational excitation in this CH stretch motion. All right, and then the last thing I just want to show you is now I'm just going to do a rigid scan. I'm going to generate geometries linearly interpolated between my reactant minima, my product minima, and my transition state. And I'm just going to do single point energies. And I'm going to show you what the curve looks like. Calculate rigid energies. So what it's doing is it's just linearly interpolating from reactant to transition state and then transition state to product. And then my script basically just looks at the output jobs and it prints out for you what's V1, what's V2, what's my V12, this is my coupling element, and what's my EVB energy. So if I then just plot these energies, I get something that looks like that, right? So this is my reactant state, my product state. My reactant diabat is the red line, my product diabat is the blue line, and my EVB potential is this guy here. So this is my fully reactive. So this is it. This is how it works. And so that's all I have to tell you about. If anyone wants to have a look at this stuff, you should feel free. It's online. You can play with it. If you have comments and suggestions, if they don't involve too much work, maybe we can help you with them. But otherwise, if you really are keen, we can add you as a dev to the project and you can contribute. Acknowledgements. So Michael Connor, Rob Arbin, and Robin Shannon, who I haven't acknowledged here, are some of the guys in my group that have worked on this. And then Andrew R. Ewing, Jeremy Harvey, and Barry Carpenter have really been of great help to this stuff over the years. And thanks a lot to people that have funded this stuff. So that's all I have.
Thank you very much. Time for questions. So I saw a few questions popping up during the talk. The total trajectories or independent walkers, right? I think this was a question related to this enantiomer.
So what? Yeah. So I'm not totally sure what that question means. The different trajectories all have different initial conditions. And so the way that we did those was we effectively sampled from the transition state with initial conditions that were sampled over the vibrational normal modes at the transition state. And so we did sort of standard normal mode sampling at the transition state in both the coordinates and the velocities. And so to generate the statistics for the enantiomer of excess, we had to generate this whole ensemble of different trajectories.
Okay, are there other questions?
So I think somebody asked how I generate the curves in the end. Let me just say that the curves that I show here on this slide are literally just, all I've done is I've just pulled these numbers out here and plotted them. Okay, so in particular, I've plotted the V12 column, the V2 column, and the VEVB column. And then I just said, well, this is geometry. So I just said the transition state, which is this one here, is 0.0. Okay, this is -10 and this is +10 because I did a linear interpolation. So that's just an index of my points. So literally all I've done there is I've just plotted the numbers here. I haven't on this graph plotted my off-diagonal coupling element because it was just too many things to put on the graph, but I could have done that.
Okay, other questions are popping up? David, can you take them or should I read them?
How do I get the red curves? What version of OpenMP do I use? Okay. So I've found that it doesn't really matter very much the version of OpenMP. However, the one that I have used, I believe, is this one here. It's just literally this one here. Where's the download? Let me just find out which one I have used. Let me see. I can check the one that I've used. I've used a lot of versions and I've never had a problem, which is why I don't specifically know off the top of my head. OpenMPI, yes. Okay, so I have used OpenMPI. Right. Okay. Yeah. And the one that I'm running this with is OpenMPI version 1.10.0, and that works fine. Yeah, OpenMPI. OpenMPI. Right. Yeah. This is what I've used. Yeah.
Okay, there was another question. Is there interface of Tinker to Orca? Can it be possible to describe proton-coupled electron transfer processes?
Yeah. So there is an interface between Tinker and Orca, I believe. However, if you want to, I don't have access to that. So if you need to get in touch with Jeremy Harvey to find out what the status of that code is, because I can't actually say what the status of that is, whether that's still being maintained or whether it's obsolete. So I'm going to have to say that at this point, I don't know if you can use Tinker with Orca. But I should emphasize that the whole point of this TINKER EVB simulation, this TINKER EVB framework, is to let you do reactive dynamics in Tinker. So, the thing that I glossed over in this talk is how do I choose my off-diagonal coupling elements, okay? And the answer to that is that I usually have to choose my off-diagonal coupling elements by comparing the energy of a particular set of geometries that I calculate with TINKER EVB to the energy at the same set of geometries calculated with an electronic structure code, okay? And then what I do is I float my off-diagonal coupling elements and I say, give me the off-diagonal coupling elements that give me the best agreement between my ab initio data and my MS-EVB model. And if you look at a couple of the papers we've had over the last few years, you'll see that's how we've done it. And that just amounts to a sort of nonlinear least squares optimization, where you basically tell your nonlinear least squares optimizer, you say, give me a value of the parameter that minimizes the total difference between a subset of energies at a particular set of geometries. Okay, so there's a question here. If one starts the simulation from a transition state point, is it required to assign an excess in energy? How much? How to choose a value of the extra amount of energy? Okay, so this question is, so that, people have spent years arguing about what's the right thing to do in this case. And I, in one answer, cannot do justice to this. So people sometimes argue that you should sample it from a Wigner distribution where you put, the 0-point energy of the normal modes. Other people argue that if you're doing classical dynamics, that's a crazy thing to do and that you shouldn't actually put the Wigner energy in there. Some people say that you should do your sampling from a microcanonical ensemble at the transition state. Some people say that you should do your sampling from a thermal ensemble at the transition state. I can't really do that justice. All I can say is that if you are convinced of how you want to do transition state sampling, then you should look at the literature and maybe figure out the way that you want to do sampling. But Tinker will allow you the flexibility. This implementation that I've shown you will allow you the flexibility to do it however you like. But as to the best way to do it, that is a matter of ongoing dispute for the last 30 years. So I don't know that I can necessarily answer that, apart from saying that this framework is effectively transition state sampling method agnostic. So it doesn't care. If you have a good way of doing the sampling, put it in there. And if you just want to start with 0, you can do that too. Okay. Okay, I'm not going to take any questions about crowd surfing and Handel's Messiah because that gets too political. Choose a value. Okay, so comparing with React's FF, how scalable and time consuming? Okay, so this is a good question. So React's FF, as far as I know, also involves diagonalizing a matrix. So the principal bottleneck for both of these methods, if you get to big enough systems, is probably going to be the matrix diagonalization, because that generally goes as n cubed, where n is the number of matrix elements. So I guess the real advantage of the advantage of React's FF versus the MS-EVB approach is that React's FF includes lots of reactions, and so in that sense it's very general. Whereas the MS-EVB approach, you basically have to construct the reactions, but it allows you much more power in making much more accurate potentials. Okay, and so that's a critical thing here, right? I mean, I've been able to, using this methodology, get results that are in nearly quantitative agreement with transient ultrafast infrared spectroscopy. And that's because I can basically tune the potentials to be as accurate as I like. And so I would say React's FF is very general, but not nearly as accurate, especially to do sort of spectroscopic levels of accuracy. EVB, not as general, but potentially a lot more accurate. And so the choice of which one you use, I think, really depends on how accurately you want the reactions to be simulated. Certainly for the enantiomeric excess problem, we needed pretty accurate potentials to make experimental hypotheses. Transition metals. No, I haven't done that. However, people do that with EVB. I have not personally done reactions with transition metals, but that is a thing that people in Arya Varshil's group and elsewhere have worked on previously. So Tinker gives molecular mechanics force fields and whatnot for transition metals. So there's no reason that this couldn't be applied to that framework. I haven't done that yet. But everything's in Tinker, and Tinker gives you the flexibility. So if you're interested, then and you do something cool, then let me know.
There was one more question. I have not understood why the coordinates must be identical but with different connectivity. What if reactant and products are structurally far?
Okay. So yeah, all right. So that's kind of a good question. All right. So let me clarify. All right. So let me just clarify here. So, okay, so you see here, the reactant is here and the product is here, and they are different geometries, right? So, for example, this distance is short here, and that distance is long here. All that Tinker does with the XYZ files is that's how it starts the simulation, okay? And so, the way to think about this is really it's the same way as you would do a conventional classical MD simulation, all right? And so if I was going to do a conventional classical MD simulation, it would make no sense to have two different sets of coordinates, okay? So my diabatic states, right, if I go back to this picture, H here, I should have written H is a function of Q, where Q is coordinates. V1 is a function of Q, V2 is a function of Q, Vn is a function of Q. And similarly, all my off-diagonal coupling elements are a function of Q. Okay, so Q always has to be the same because there's only ever one geometry that things can be operated on. Okay, so the really important thing here, so if I was going to go back, so what we tried to do in designing this EVB-enabled Tinker was really to do the minimal perturbation required so that people who know how to use Tinker could stick with the Tinker philosophy and do EVB simulations. If I was to go back and write my own MS-EVB code from scratch, which would be a lot of work, which is why I don't want to do it, then what I would do is I would probably just have one coordinate file, okay, because there is only one geometry. What I really only need are two different connectivities. That's all I really need. However, we made a philosophical decision here to do the minimal perturbation required, right? Which is why we opted to do it this way. So as I said to you earlier, if you don't put identical coordinates in, Tinker will complain and it will crash and it will tell you have to have the same coordinates. The important thing is just the connectivity, because the connectivity basically tells you, okay, well, tells you what the nature of your diabatic states are. So if that's not clear to you still, then what I would encourage you to do is to look at the problems where I optimize the reaction, the reactant, and the product. Those two examples that I had in the directory. And if you do those, you'll see that it will go to the appropriate reactant and the appropriate product, always with the same set of coordinates, right? You never have two different sets of coordinates. The thing that determines your potential topology and what the nature of your diabatic states are is really the connectivity, right? Or what you could call the topology. Okay, when should MS-EVB be used over QMMM? So I gave examples of that at the end, right? I said I gave a lot of, so maybe you weren't here for that, or maybe you came in late, but you know, there's a lot of reasons why we couldn't use QMMM. So the first thing is that, you know, whenever you have anything with multi-reference character, like we did in this CN problem, so CN plus cyclohexane in an organic solvent, I mean, QMMM just absolutely fell on its face owing to the multi-reference character in the CN radical. So it's, you know, nothing really worked well. In the fluorine plus CD3CN reaction, here you'd have a scenario where if you were to do it QMMM, you would need to have a dynamically changing QMMM boundary. And that just gets extremely messy. It never conserves energy, and then your dynamics are effectively meaningless dynamics if they're in the non-equilibrium limit. And in the enantioselective dynamics reactions, okay, we could do one or two, we could maybe do 10 QMMM trajectories, but to actually make a computational, make a hypothesis that was experimentally testable, to generate statistically meaningful results, we needed to run literally, you know, tens of thousands of trajectories, and that just isn't possible with QMMM. So that's the case, and the other thing I mentioned is that QMMM is extremely bad at treating non-equilibrium energy flow. So if all you ever do with QMMM is umbrella sampling or some sort of equilibrium sampling method, probably okay. If you ever want to do anything that's in a non-equilibrium regime and you actually care about the energy transport rate, QMMM will almost always give you the wrong answer because you get relics that are introduced into the energy flow dynamics owing to the fact that you have this perturbation where the QMM region couples into the MM region. So in all the systems that I've described here, energy flow is an extremely important thing because we were looking at systems that were very far from equilibrium, in which case QMM simply wasn't adequate. So yeah, what information was obtained with these simulations for the case of potential energy bifurcation? So that was really this plot here, and the paper's here. You can look at this paper, this PCC paper from 2015, and you know, it was really the fact that solvents appear to computationally screen, solvents appeared to actually promote enantioselectivity owing to their chirality. And there's a lot more information here, and we actually have another paper that's coming out soon to analyze specifically what solvent interactions are responsible for this large enantiomeric excess. But you see here, to get this data, to get these error bars converged down to a point where we could actually have meaningful statistics, we literally had to do thousands of trajectories. And the way that we did that error analysis is, again, described in this paper. So I would encourage you to have a look at this. This is something that just would not have been possible with QMMM. Okay, all right. I don't see many more questions.
Thank you, David.
Okay, one more thing I can just deal with. So I might need to start with some weird starting connectivity for the reactant. No, you shouldn't need to. So the way to test this is literally, if you can do a Tinker simulation for a particular state, reactant or product, just one standard serial Tinker, then you can use that as a connectivity. Okay, it was referred to the old connectivity question. All right, you can, but literally, this is a good point though. I just want to repeat this. You can literally, if you can do a connectivity in standard serial Tinker, you should literally be able to take that connectivity and put it in the MPI version and use it as a diabatic basis state, and it should just work. Okay, so that's all you have to do is literally copy and paste, make sure the coordinates are the same, and everything should be fine. Okay, all right, I think I'm going to check out now because that appears to be it. So thanks very much.
Thank you, David, for your time. I will stop the recording and